Hello, physics class. Glad to be doing this for you. This is the lesson for Tuesday. That would be April 7. Today, I wanted to spend a minute or two just quickly reviewing what we covered on Monday in our live class. And then we're going to actually get into talking about the two kinds of waves. I have recorded a demo that I'm going to try and throw into this video by doing a screen share, and hopefully it will help. And then maybe talk about standing waves. I'm not real good with explaining the concept of standing waves, but I'm going to go for it anyways, especially through this, much harder medium to communicate with. It's really hard to gauge whether you guys are really with me. That's probably why you find me asking, hey, are you with me? Give me a thumbs up. So why not make it harder and choose something that I'm not real good at explaining and try to explain it to you this way? I just thought it'd be fun. Actually, I'm realizing I need to get my tuning forks, because tuning forks actually help us understand one of the kinds of waves. So I'm back, got my tuning forks. Here they are. I'll set them aside, and we'll hopefully use them a little bit later in class. So first, what I'm going to do is just say, I hope you're doing well. I appreciate you guys, and I appreciate your hard work. Now I'm going to share a screen with you. Let's share a whiteboard just for fun. Share a whiteboard with you, and let's review. We learned about the fact that there was a baseline to a wave. Let me do a little bit of drawing here. We learned that there was a baseline to a wave, and that's essentially the point where we measure all of our waves off of. So we can measure the amplitude of a wave, and the size of the amplitude actually has something to do with the amount of energy a wave carries, because remember, that's what waves do. Waves carry energy, and the amplitude could also be a measurement of the baseline to the bottom of the trough. So we got crests and troughs here, crest. Put a C there for crest, put a T here for trough. And then we've got wavelength, the actual physical length of the wave. The longer it is, the shorter it is, measured in meters. And I believe we talked about a sound wave that was around 260 hertz. This is a 256 hertz tuning fork. It's actually middle C on the piano, I believe. And we said that the length of the wave is something like 1.2 meters, if I remember correctly from the calculation that we did. Right, and then we talked about frequency, the number of cycles per second, or the number of hertz that are there. And so that's how many waves there are in a location. Right, so there you go. The top picture that I just drew for you is like one wave in a certain distance, and this one's 1, 2, 3, like 3.5 waves in the same distance. So this right here is a higher frequency. Look at how bad I write and how awkward this is. I apologize. So this one's a higher frequency. The wave on the top is a lower frequency. So that's kind of our review. Now, the one thing that I do want to make sure I review with you again is the formula for wave velocity, because we're going to have some situations where you got to calculate these. Now, I know this is not the ideal way to work out calculations, because we usually do calculations on paper, on tests, and it works out really well. You guys have space to crunch numbers. We're just going to have to do calculations in multiple choice sections so you can calculate it, find the answer in an ABCD choice. So let's go over the formula again. Wave speed is going to be the frequency represented by F multiplied by the wavelength with this, which is this crazy cane with an extra foot, as Coleman told us about it. Actually, that's the Greek letter lambda. So frequency times wavelength, and that's going to give us an actual meters per second rating when you actually work out the units and the math on that. So let's do a little different formula here. Again, let's use a sound wave. This is 256 hertz. This is essentially middle C. But if we were to actually go up an octave and stick with the speed of sound being around 330 meters per second, and we were to go up in frequency, up one octave, the frequency of the C, one octave above middle C, would be around 512 hertz. So if we want to find out the wavelength, right, that crazy looking upside down Y lambda thing, right, we have to use those two numbers to figure out the answer. So what we do is we divide by the 512 on this side and do the same thing over here, divide by 512. I do not know how the guys on Khan Academy make writing on these things look so easy, right? So essentially you've got 330 divided by 512. I'm gonna get out my calculator, which is on my phone because I don't have a regular one here. 330 divided by 512, and we're gonna get an answer. But if you have logical thinking skills and you're remembering that 256 hertz was around 1.2 meters from our previous class, if we double the frequency, the wavelength should go down in size. That's a basic inversely proportional relationship. And since we've doubled the frequency, you're probably thinking inside your head, the wavelength should probably go down by about half. So if we do the math, the wavelength does come out to be basically it's hard to do decimal points, 0.64. That's what my calculator punched out with those numbers, give or take a little bit, considering what we're doing from memory and what we used in the class, in the live class on Monday. So that's review. So let's clear this off. So we might come back to it. And let's stop sharing this screen and let's get back to the talking head that is staring at itself instead of staring at the camera. So today we want to handle some new stuff. And pardon me, I threw on a tie with a shirt for a different change of scenery for you, and it was annoying. It's annoying me now. So we're gonna go with the tie headband for now because I just can't do it anymore. It's too tight on my neck. I've been eating too much in this quarantine and I'm getting too big. Okay, so we're gonna move on to some new stuff. We're gonna talk about the types of waves today, and we're gonna talk about standing waves. Standing waves is like a unique wave situation. So let's talk about the types of waves. There are really two kinds of waves. There's a transverse wave, which we represent with AT, right? I'll try to explain this to you. And then there's also what are called longitudinal waves, which we represent with two lines that are going like this. And I'll explain that to you in a minute when we get to a shared document, or actually just a screen where I have some typing and stuff. I'm not sure I have the document shared with you. But transverse waves and longitudinal waves, they make up basically every kind of wave out there. So let me get to the right place. Here we go. Now I can do a screen share for you. Screen share to Google Chrome with the types of waves. So hopefully you can see this. First kind of wave is called a transverse wave. I'm gonna kind of highlight it here, and I'll highlight it in yellow just for fun. And I'll read you the definition because I would state it to you in a normal class, and this way you can be insulted by me reading things to you from a distance. A transverse wave is a wave that transfers energy, all waves transfer energy, through a medium. Right, so these waves need a medium. There's only one kind of wave that I know of that doesn't need a medium. We're not talking about that here. But the medium is the material that the wave moves through. So the sound waves that you hear coming out of your computer speakers or your iPad speakers, they're traveling through air. Air is the medium. If I was to whack this tuning fork, you probably heard a faint middle C there. That sound was leaving the tuning fork and traveling through air to the microphone of my computer. So that's the medium. Now, ocean waves, the energy travels through the water in the ocean. All right. The ocean water is the medium, right? That's the material that the wave energy transfers through. So here we go, transverse wave. A wave that transfers energy with the medium vibrating perpendicular to the direction of energy travel. And that's why I said perpendicular, right? And I used a T symbol. If you remember from geometry class, the upside down T is the perpendicular sign, right? So what you've got is, in this case, right, I just use it as a T to remind us of transverse with a T. And the medium is going to vibrate up and down, up and down, up and down, while the energy wave travels perpendicular at a horizontal motion to it. Okay, got to get rid of the tie. That was bugging my head. So the medium goes up and down, up and down, up and down, and then the energy goes horizontal through the medium. Now this is actually really kind of cool. I learned this years ago, many years later than I should have, from my father-in-law. I was out on the boat and we were in some little waves, but we weren't really moving anywhere. I said, how come we're not moving? He said, well, because there's no wind. There's just little waves, but there's no wind. Every other time we'd been in the boat would blow from place to place when we had the engine off, because the wind would blow us, but we were actually just bobbing up and down, up and down, up and down, and not really moving much because there was no wind. And he explained to me this concept that the boat just rides up and down with the vibration of the water. And he said it's something that they used to do before GPS units on and fish finders on boats. They would take a water bottle. This isn't a water bottle. This is a bubbly bottle, bubbly can. But they take a water bottle and put some water in it, and they would have it floating with just this much sticking out, and they'd throw it in the water where they found a hot fishing spot. And then if they blew away from that spot, they could just, turn the engine back on and drive back up to where the water bottle was. And the water bottle just bobbed up and down, up and down, up and down in that location, and it didn't blow away because the water bottle is moving with the medium, and the energy is traveling. The actual water waves don't travel anywhere. Okay, so water waves that we represent with, the math sine waves, those are transverse waves. The energy moves horizontally where the medium moves perpendicular up and down to that. So we could take a rope and we could shake the rope up and down. I don't know if you've ever done this, with an electrical cord. It's all tangled, so you spread it out and you start shaking it up and down, and it goes up and down, and it kind of uncoils itself. You're just making a transverse wave when you're shaking it up and down, making crests and troughs. Ocean waves are like this. Let's see what else are other examples of this. Actually, light waves, even though we can't see them, and technically light waves don't need a medium, but they're actually going to be transverse waves. So those waves, they all have that perpendicular motion of material versus energy. So that's an important concept for us to understand. The next kind of wave is this longitudinal wave. I'm going to highlight that in green for fun, for a different color. And that is a wave that transfers energy with the medium vibrating parallel to the direction of energy travel. Forgot a word there. A wave that transfers energy with the medium vibrating parallel in the same direction as the energy travel. So I like to represent this with parallel lines, because what you've got going on is, and I'll just shift it this way. What you've got going on is the medium is vibrating back and forth, back and forth, back and forth, but the energy is traveling in the same direction, right? Back and forth, and the energy travels in that same plane, in that same direction. This is sound waves. Now, if I had a slinky, this would be really easy to illustrate. If you have a slinky, stretch it out on your kitchen floor, really, really, really long. And then what you do is you just kind of start shaking it back and forth, and you'll see little compressions, right? And spread out areas, compressed areas and spread out areas that are going going back and forth in the slinky medium. So that's a longitudinal wave. Now, transverse waves, they're represented by the typical sine curve, like we talked about, crests and troughs measured off of a baseline. Longitudinal waves are different. Longitudinal waves, since they aren't having up and down movements, everything is in the same plane, they have what are called compressions and rarefactions. Maybe I spelled that wrong. Rarefactions. Compressions are where the actual matter, the medium, actually compresses closer together, and rarefactions are where they spread apart. So compressions are medium compressed closer together, and rarefactions are where the medium is spread apart. Now, if you stop and think about a tuning fork has these limbs that actually can vibrate back and forth, back and forth, back and forth, back and forth, back and forth. And what they're doing is they're smacking air molecules. So what they're doing is the limb smashes air molecules here and compresses it, and then these ones go out, and these ones go back. So they compress, and then they rarefract, compress and rarefract, compress and spread apart, compress and spread apart. And so they compress and spread apart, and then compress and spread apart. And they just keep traveling down that way. And so it's not necessarily the easiest thing to see or to understand. But what I've got is I've got a video. This is me taking a video of how a tuning fork works with my kids. And we can talk about this more. I had to switch the screen, so now I'm going to share screens to this video. It's Mr. Hicks' iPhone recorded video. On my front porch, you can see my kids. I am definitely not dressed quite appropriately. I'm in jeans and just a white t-shirt, showing off my casualness in this quarantine period. So I think you'll be able to hear this. I'll jack the volume up. So try to watch this, and hopefully you'll get it and understand it. Okay, my physics class. This is Mr. Hicks. Got my kids here with me, just so that I'm not talking to, you know, nothingness. But I wanted to do a few demos for you. This is for Tuesday's class. I've got a large tuning fork here, which makes sound wave, and I have an equivalent smaller tuning fork here, and a glass of water. This is to try and illustrate something. I just thought I would show it to my kids. We'll talk about this in actual greater depth tomorrow when we actually have class. I'm recording this on Monday. All right, so here we go. This is a tuning fork. It's attached to a sounding base, and it actually will vibrate with the tuning fork and put out a noise. I'm not sure you're going to hear this very well, but you're not going to see the movement of the limbs too well easily either. So Maddie and Jackson, look here. Can you see the limbs of the tuning fork vibrating? Yeah.
Very blurry.
You may not be able to see it real good, but there is a blur there. All right. You might be able to hear that noise. There's a blur if you're up close to it. Okay, so we talked about longitudinal waves. Longitudinal waves are ones that actually create back and forth vibrations that are in line with each other. And that's what a tuning fork does, because these limbs are hitting air molecules going back and forth, back and forth, back and forth. Now, since that's hard to see, what we can do is make them run into something that we can see. We can't see the air molecules that this thing's running into, but we can make it see the water molecules. So not to get that wet, pay attention, son, we're going to stick the tuning fork down in the water, and hopefully you will see the splash. And that's the point, is the vibration of the tuning forks are actually back and forth, back and forth, back and forth, going to shoot water molecules out. So here we go. 1, 2, 3.
Flash.
We'll do it again. 1, 2, 3. Get in there close. All right, so that's a demo. I'll see if we can work this into the video or show it tomorrow in class. Hope you're gonna have a good one. Bye. All right, so I hope that went through. If not, you just had 2 minutes of staring at my face, staring at my screen, and nothing going on. But I think it did work. I've seen other teachers do this. So that is a demonstration of a sound wave, a longitudinal wave, and the vibrations back and forth, back and forth, back and forth. We're compressing and spreading out and compressing and spreading out. And the water shooting is where you see the actual limb doing something. You can't really see them vibrate that much, right? Because they move so fast. 256 hertz. I don't know if you can see that. 256 hertz right there. 256 times a second. That's pretty stinking fast, right? So what it did was it's whacking the water molecules, and you could see the water molecules shoot off. So that's giving you the idea that there's compressions and rarefactions there. Okay, so we've covered transverse waves, right, which we represent with a T. Longitudinal waves, which I represent with the parallel line symbol, right? Kind of actually reminds me of a tuning fork, parallel lines, like in geometry. And that's two ways that energy is transferred via waves. So now I want to get into this concept of a standing wave. And so if you're wondering about standing waves, what I would do is recommend you to look in your book, page 380, 381. Again, this is not my strongest point here. And a lot of times I kind of skip this because there's so much information here. But we've got a little bit of time. So we're going to talk about standing waves. Standing waves. Hi, Jackson. I'm recording a video. Please go. All right. Standing waves are a situation where you can mess around with a rope. And what you can do is you can actually shake a rope and it goes up and down, up and down. Well, if you start shaking a rope and you shake it at just the right speed, with just the right frequency, what you can get is you can get, and I'm going to try and screen share a whiteboard here with you. If you shake a rope at just the right speed, you can get the rope to kind of like stay in this exact shape. And there, what happens is you shake the rope and you send the wave this way. But if it's attached to a wall over here, the rope energy hits the wall and then bounces back. But if you actually get the frequency right, you'll have a permanent high point and a permanent low point that stay there in this middle section, which is actually called a node. That middle section never moves. Right? So what you do is you get this like wave that just keeps going back and forth over itself, and you get this wave that just kind of stays in place and vibrates up and down, and the wave energies continue to go back and forth, but it doesn't look like the wave is even moving. Like there's always a crest and always a trough, and this middle part never moves. That node, it stays put. Your book talks about how you could actually pinch that middle spot and the wave would still go through. It's really quite interesting. It's a standing wave. Now, where you actually see this a lot is or maybe hear it would be better, is you actually hear this with sound waves. And I know, okay, Mr. Hicks just told you that sound waves don't look like this, but we actually translate sound waves into transverse waves for the purpose of visualizing them. But if we were to take a sound wave and translate it into the transverse look, the sine wave with the crests and the troughs, a sound wave that is in like the pipes of a pipe organ, the sound waves are going up and down, right? And they're actually vibrating in sync with each other and creating these standing waves, and they actually kind of like amplify in the pipe organ tube. I'm sure most of you haven't really been exposed to a pipe organ. It's a really old instrument that most people don't deal with very often. But another place where you can get these standing waves, where the waves are perfectly in sync and they just have this node that's created, is if you were to like blow into a pop bottle, Coke bottle. You guys ever take a bottle and go over it, and you can get a note? Well, do that with a glass bottle, and you can get a note, maybe even a plastic bottle. Glass seems to work really well. And you can get this note that's produced. Well, what's happening is you're putting out waves, and those waves are standing in the same location, and they're vibrating, and there's a node in the middle. And so what it does is it just kind of builds up this sound wave. And so you got this concept of a standing wave. It happens from time to time. It's kind of interesting. So that's our two kinds of waves. In our next class, we're going to be trying to work on some concepts outside, trying to do some wave lab type stuff. Maybe I'll see if I can show you a standing wave by shaking a rope. But I also thought that in our next recorded session on Thursday, we would talk about the concept of interference. So that's really a neat topic as well. So now I'm going to stop screen sharing and just say, I hope you're having a good day and doing well. I hope we're staying on top of everything. Please make sure you communicate with me if there's anything that I've messed up or something you don't see on the LMS or something I can do to help you. I'd be glad to do it. Have a great day. This is Mr. Hicks signing off.